So it's 9 a.m. GMT now, and welcome everyone to the third day of the SAZERAC 21 centimeter GULP. And this is the first session of the day and the first session on analytical and numerical modeling of the signal. I am Sambit Giri, a postdoc at University of Zurich, and I will be the chair of this session. I want to remind everyone that we have a dedicated Slack channel in the SAZERAC Slack workspace. It is called 21 centimeter 2022 3A. I strongly recommend everyone to post their questions in the Slack channel as a thread corresponding to the relevant talk. You can also post the questions here in the Zoom chat. For everyone watching later, it's also a good opportunity to post their questions in the Slack channel, and I request the speakers to answer them whenever they have time. I will keep an eye on all the questions and ask the speakers after the talk to answer some of them. So our first speaker is Anastasia Fialkov, who will give an overview talk on theoretical modeling at high redshift. Anastasia, if you want to share your screen.
Hello, everyone. It's nice to be here virtually.
And I will give you a 5-minute warning.
Okay. Do you see my screen?
Yes.
Okay. So overview modeling that has been done by my group. Of course, there are many groups in the world, but I'll focus on what we have been doing in the last couple of years. So thank you for the invitation, and it's very nice to be here and talk to all of you, even though virtually. So focus on the modeling of this 21 centimeter signal from high redshift universe, mostly focusing on cosmic dawn, and then giving a very brief introduction because we're all experts here. So the high redshift universe, I will be focusing on the epoch of cosmic dawn, is the very interesting epoch that we have very little understanding of so far. And that's the epoch when the first structures were formed and the first population of stars appeared and emitted photons in different bands, including the UV, X-rays, so enabling effects such as Lyman alpha coupling of the 21 centimeter to the temperature of the gas, making it observable signal. And then the processes such as X-ray heating by binaries or other X-ray sources, which drive the signal from absorption into emission. And then finally, the onset of reionization when the signal goes to zero as more and more hydrogen is ionized by the UV from stars. So of course, we know that the signal is expected to be both varying in time as in the average of the universe, but it also fluctuates on different scales driven by different processes. And also, if you look at the same signal at a given redshift, it could be dominated by different processes at different scales. For example, Lyman alpha coupling would affect the signal within 100 megaparsec around the source. UV photons would affect it on much smaller scales at those times, just around the star forming regions, while X-rays can drive the signal on scales of up to gigaparsecs, actually, so very large cosmological scales, so up to the size of the universe at those times. So it's very interesting to study how the signal fluctuates and evolves when we look into these processes into more details. And that's what we were trying to do with my group and collaborators. So we were looking into more subtle effects, such as, for example, multiple scattering of Lyman alpha photons that is usually ignored in semi-analytical modeling, or metal enrichment of the medium and the evolution from population 3 to population 2 stars. We also looked at the effect of high redshift radio sources, which is related to the edges signal. So I will mention all these developments in my talk now. So of course, we know that the 21 centimeter signal is in itself a subtle process. For example, the line alpha coupling is a very, also let's say, fragile effect. It's atomic physics and how the atom transitions between levels and drives the hyperfine splitting transition. But there are even more subtle processes that I'll mention today. For example, line alpha heating, and including this effect turned out to have a huge impact on the range of possible signals that we explored. For example, the gray models here that I'll also explain a bit more in detail later show the signal without taking into account the line alpha heating, and the blue models are with. So we see that there is strong effect of line alpha heating on the parameter, on the range of the models that are allowed. So first talk about the physics of line alpha photons, and it's of course a well-known effect, Westhausen field coupling, which means that hydrogen atom, the spin temperature is coupled to the gas kinetic temperature by the presence of line alpha photons, so that they can be absorbed and then re-emitted, and the atom ends up in another hyperfine state as previously, or in the same one. So the Westhausen field coupling affects the distribution of hydrogen atoms and drives the 21 centimeter line. So thanks to this effect, the signal becomes observable as soon as stars form. So before the star formation, we are in the what is called the dark ages, and the signal is mostly driven by the CMB and collisional coupling. When collisional coupling becomes inefficient, the signal nearly disappears. And then as soon as stars produce line alpha photons, they enable this Westhausen field coupling, and we can see this deep absorption feature in the 21 centimeter signal. I don't know if you can see my cursor. So it couples the spin temperature to the kinetic temperature of the gas. So this is of course well-known effect, and is usually included when modeling 21 centimeter signal, or at worst case, this coupling is assumed to be saturated, meaning that the 21 centimeter spin temperature is fully coupled to the temperature of the gas. In reality, it's a gradual effect, and it takes some time for the gas to become fully coupled, spin temperature to become fully coupled to the gas temperature. So this signal will vary, and the rapidness of coupling will vary as a result of, as a function of cosmological and astrophysical parameters. For example, if you change the properties of the first star forming regions and star formation efficiency, this coupling can happen earlier, later, be faster or slower. But line alpha photons have several other effects that can impact the 21 centimeter signal. For example, they can heat or cool the gas, and this effect was explored early on. So for example, there are papers from 2004 and 6, 7 by Chen, Miralda Escude, Pritchard, Furlaneto, Chuju and Shapiro, and also Chris Hirata. So they already then noticed that line alpha photons can heat or cool the gas because they can couple, basically, well, they exchange energy from the radiative field to the gas kinetic temperature. So they couple the gas temperature and the spin temperature at the same time. So there are two competing effects. Continuum photons, these are photons emitted between line beta and line alpha. They can redshift into line alpha line and heat the gas. And here on the top panel, you see the distribution of this. You see the line alpha line profile around the line alpha line profile, and this is the energy lost by photons around line alpha line, which is gained by gas in recoils of atoms when line alpha photons scatter. but also injected photons can cool the gas. And so injected photons are those that cascade from high atomic levels, and they can cool the gas. And on the bottom picture, you see the distribution of this injected energy around the line alpha line. So orange is the part that goes into cooling, and the green one is into heating of the gas. So overall, line alpha can both heat and cool the gas, and this is a temperature dependent effect and also redshift dependent. So overall, mostly they will heat the gas because cooling kind of compensates for itself. So the injected photons will have very small effect compared to continuum photons. There is a similar effect of CMB heating introduced recently by Van Madhav et al. In 2018. And this is basically transfer of energy between the radio background and gas, also mediated by Lyman alpha photons. So as soon as we have Lyman alpha photons produced by stars, we will have Lyman alpha coupling of the 21 centimeter temperature to the gas, but we'll also have this effect of heating that the stars actually create. We explored this in a recent paper with Tamaris and Renan, and we looked at how this Lyman alpha heating compares to different other components. For example, Hubble expansion, cooling. This is a green line here. The light blue is the heating termed by continuum photons, and the dashed blue is the injected cooling rate by cooling rate by injected photons, and the red one is the CMB heating. So we see that at very high redshifts here on the left, CMB heating can be more important than the Lyman alpha heating, but it's still smaller, has a smaller effect than the Hubble expansion, while on the lower redshifts, Lyman alpha heating can dominate over the Hubble expansion rate and become more important, while CMB heating becomes less significant. Overall, the Lyman alpha heating effects can contribute to the increase in the gas temperature by 100 Kelvin, which is significant over the cosmic history. But we do need significant Lyman alpha background in order to create enough heating to be significant, and so it mostly manifests itself at lower redshifts. So this kind of leads to conclusion that the commonly used saturated Lyman alpha coupling limit when the gas is hot, when the gas is cold but fully coupled, it's not really physical in the presence of Lyman alpha heating, because as soon as Lyman alpha coupling is enabled, so is the heating effect. So the temperature of the gas will rise above the adiabatic cooling limit. So on the bottom panel, you see how thermal history progresses in these models, and the solid line is the full case when we have both Lyman alpha and CMB heating taken into account. And dashed line is when we ignore these heating components. So we see a dramatic change just by the subtle radiative effects. In these models, we disabled X-ray heating to see what's the impact of Lyman alpha and CMB heating on the gas temperature R. And then naturally, they will affect also 21 centimeter signal, both the power spectrum and the global signal, just because they affect the gas temperature. So again, without these effects, you can see on the global signal panel in the bottom right corner, the gas, the 21 centimeter signal goes as deep as minus 200 millikelvin, while just enabling these subtle effects, we can get only to minus 150, and the absorption trough is shifted to high redshifts. So because it's physics of Lyman alpha photons, they have their mean free paths, and they will hit the gas only close to the source, so around 100 megaparsecs, in 100 megaparsecs region. So it's much shorter scales compared to hard dish X-rays, which can propagate to a few hundred megaparsecs. And so this will increase fluctuations in the 21 centimeter signal at around 100 megaparsec or few tens of megaparsec scales, as we see on the top right panel. This is also a relatively late time effect because, again, we need a considerable amount of Lyman alpha photons to have significant heating from this effect. So I showed this plot earlier. This is a kind of parameter study that we did with Lyman alpha heating and CMB heating enabled. And we see that there is a strong impact on cold scenarios, and we don't get this very deep absorption signals just by including the subtle heating processes. We have also a strong effect on the power spectra. In this work, we also included multiple scattering of Lyman alpha photons. So traditionally, at least in what we used to do, was to assume that Lyman alpha photons propagate along straight lines from the source. And so they would hit the gas in a shell around the star-forming regions with the radius of the mean free path of Lyman alpha photons that we calculate in the simulation. However, in reality, Lyman alpha photons scatter multiple times. They're absorbed and re-emitted because it's the hydrogen line. So in reality, we would see a picture more close to the scenario on the right here, bottom right, where colors, that's just a window function in the simulation. That means that Lyman alpha photons would scatter everywhere around the source. And so we implemented as a Monte Carlo process, drawing both direction of an angle and distance of the scattering between scattering events from a distribution. And so now we have a distribution of radii where the Lyman alpha photons can scatter, and you can see it on the top here. So overall, there is a shorter path compared to no scattering of Lyman alpha photons in medium. And the effective distance, effective horizon of this process is a few tenths of megaparsecs. So a bit smaller than if you assume just a straight line propagation. And of course, this affects both the global signal and the power spectrum, having a more stronger effect on the power spectrum. So here are some snapshots from the simulation. So the main effect is that there is smoothing of signal on small scales. So below the effective horizon of Lyman alpha scattering, there is just a kind of washed out fluctuations. So on the left is without Lyman alpha scattering, and on the right is with. And we also see there is more clustering because the photons propagate to shorter distances than without the multiple scattering. When we look at the power spectra, we see a stronger effect. So we see some effect. So the solid lines are with Lyman alpha scattering, and dashed lines are without. And so we see some enhancement in all cases. So we looked at several different values of star formation efficiency and X-ray heating efficiency. And so in the case of very weak X-ray heating, we see this impact of Lyman alpha scattering in the power spectrum all the way through cosmic history from high redshifts to low redshifts. And this is because at high redshifts, the 21 centimeter signal is affected by Lyman alpha through Wolfshausen field effect, while at lower redshifts, it's the Lyman alpha heating that creates this enhancement in the fluctuations. So when we take a higher value of X-ray heating efficiency, it dominates at lower redshifts over Lyman alpha heating, and we do not see the signature of enhancement due to multiple scattering in the simulations. So that would be just high redshift effect. The impact on the global signal is much weaker, so I don't show it here. So as a result of this multiple scattering and enhanced heating effects, we would see stronger Lyman alpha coupled bubbles at high redshifts than previously thought. And they might be directly observable, for example, by the SK. So you can see on the right here a picture of the slam alpha coupled bubbles at cosmic dawn. We also looked at the effect of variable star formation efficiency. So we know that in reality, every galaxy has a bit different feedback processes, and star formation can vary. Star formation efficiency can vary between different galaxies, even if they are of the same mass. That's natural for our universe. But we used to assume in our simulations that all halos would form the same number of stars, the same stellar mass, given the same halo mass, and being in the same overdense region. But in reality, it might be different. So every star-forming halos could have their own merger history or their own environment, for example, being in a more in a dense region or low or a region with stronger Lyman-Werner field. And so star formation efficiency would be less efficient or more efficient depending on this environmental properties. So we implemented a stochastic star formation efficiency in halos, and here you can see how it impacts the 21 centimeter maps. So on the bottom, on the top left is our old case where all halos form the same number of stars. And then we added both a Poisson process in the generation of the number of halos and this variable star formation efficiency. So with strong variation in star formation efficiency, we see much stronger fluctuations in the 21 centimeter signal. So that's an, okay, thanks. Interesting process to explore. And it also is not only high redshift effect, it can also be the signature of this variable star formation rate will propagate into our X-ray heating, and also ionization would be more stochastic than we obtained previously. Of course, it's a very uncertain process, and the kind of width of the probability from which we draw the star formation efficiency is highly uncertain. So we calibrated it to numerical simulations such as by Hu et al. 2016. We also looked into effects of POP3 IMF, so initial mass function of population 3 stars and the transition between population 3 and population 2. And I'll only flash some of the results because Thomas Gacy-Jones will be giving a talk on that later. So Thomas did a great job implementing a realistic population 3 spectrum of stars and integrating of the initial mass function. He'll explored different shapes of initial mass functions, and I'll just briefly show you the result and move on, because that will be in Thomas's talk later today. So you can attend his talk and learn more about the effects of initial mass function on the 21 centimeter signal. We also looked at the transition between population 3 and population 2 stars. So we know that first stars were formed from metal poor gas, so metal free gas, and then first supernovae enriched this gas by heavier elements, leading to the change in the mold of star formation. So if population 3 stars are thought to be very massive, then population 2 stars, due to more efficient cooling, could be much smaller, and their properties, mass and lifetime, could affect the emissivities of the stars and the spectra of the stars. So with Matis Mag and also Itamaris, we looked at the transition between population 3 and 2. So we used an N-body code coupled to the semi-analytical code CodeA-Sloth that tracks star formation and metal enrichment. We built a model that follows the fraction of population 2 versus population 3 star forming halos based on that code, and then coupled it to our 21 centimeter simulation to explore the effect on the signals. So it's all in this paper, which is now online, and you can see that taken the details of this transition, for example, how quickly the gas bounces back from a halo after being into a halo after being expelled by supernovae, would affect the details of the 21 centimeter signal. There were previous works by Jordan Miroka and his collaborators who looked at this effect. We took a bit different path here. So, yeah. Then another effect we looked at, and I will just briefly note here, just 2 more minutes, some bit. So it's what happens if there are radio galaxies at high redshifts. We know that today galaxies can be radio loud if there are quasars, for example, or AGN. And there is no reason such galaxies wouldn't exist at high redshifts. So there might be some additional radio emission produced at high redshifts. So if there are radio galaxies, they would deepen the line alpha couple of bubbles just because they produce more background radiation. So on the right here, you see what happens if there is a radio galaxy inside each star forming region. The bubbles, just the contrast becomes larger. There is an effect on the global signal and power spectrum. Even in the case when this radio efficiency is kind of in the similar range compared to today, there is some signature. And we explored how these models could be compatible with edges in this paper by Rees, myself, and Renan. So we, again, I'll just show you some results very quickly. There will be later talks by Stefan Heimersheim on how these models are constrained by Hera, recent upper limits from Hera. Stefan will go into details, and we can also constrain these models with telescopes such as SARAS-2, and there will also be a talk by Harry Bevins later, I think today, or Harry's in audience, you can ask him. So I'm not going into details, and I'll like to stop here. So I showed you that we have implemented several interesting effects that are subtle, such as Lyman alpha heating, CMB heating, or gradual methanol enrichment, and population-free initial mass function, but they do have significant impact on the 21 centimeter signal, and hopefully we can use the 21 centimeter in the future to learn about all these processes. And also there are interesting constraints from existing telescopes on models with enhanced radio background in our case that we explored. Thank you very much. Yeah.
Thank you, Anastasia, for this very nice talk. If you have any questions for Anastasia, please post it on Slack, and I will ask them here. We have a few minutes. I have one question. This method of implementing multiple scattering due to Lyman alpha, what do you do? Do you always do this MCMC method, or do you derive a filter that you use later to do your simulations?
We derive the filter, so it's a kind of window function, which previously was just like a shell, and now it's more spread, like I showed here. So it's pre-calculated window function that you see here on the right, that we can just upload as simulation is running and apply it to the.
Right, so there is no extra computational time overhead due to this. It's the same, just a new filter. Yes. I don't question it. So I have one more question. In your pop 3 stars work, for pop 3 stars, do you only use, like, assume that they're small in small mass halos, that's it, or do you assume something else, like they have a different escape fraction or some different astrophysical process?
So how we model this population
yes.
3 to pop 2 transition is that population 3 stars would form only as soon as halo crosses star formation threshold, it will start forming POP3 stars. But this will form in a burst and only once, because as soon as one of them explodes as a supernovae, right, the gas is affected. So either it's immediately enriched or expelled from the halo, and then when it recollapses back and halo starts producing stars again, it's out of enriched gas, and that will be a population 2. So as soon as so the gas, when gas recollapses, we explore how fast the gas recollapses by taking the several models: fast, intermediate, and slow recovery times. And so just we will delay the onset of population 2 star formation.
Right. So you have, in addition to the mass, you have another free parameter that controls.
Yes, here
properties.
Exactly. Here we can study how the signal is affected by this recovering time of halos, and there are signatures. We haven't explored yet the full, spectrum of models varying both star formation efficiency and this recovery time. So we don't know if that just that can be extracted from measurements and what's the degeneracy. So we haven't fully explored it yet. But just by looking at the several models, there seem to be unique features, like the slope of the signal is different. And also Jordan explored these aspects in his work with Richard Mebane as well, and Steve Forlanetto. So they find similarly that signals can be steeper in certain scenarios, and that could be distinctive feature, but I don't know yet if it's fully degenerate with other parameters.
Thank you. I don't see any more questions yet. So maybe, and we are in the break time already. Please post your questions anytime in the Slack channel, and as I said, please can answer them there. So let's go for a 15 minutes break now. See you all in 15 minutes.
Thank you, Sandip.
Thank you. If you are still here.
Me?
Stefano?
No,
Stefano.
Thank you. Stefano?
Yeah, can you hear me?
Yes, I can. I was wondering if we could test your screen sharing.
Sure. Sorry, I was muted. I was flying, but I was muted. Let me see. Keynote. Where it is. Well, let's just share the screen and go in here. Can you see my screen?
Yes. Can
you see presentation mode?
Yes. Perfect. If you want to check your transition.
Yeah. That was just, yeah, cool.
So see you after the break.
Okay, shall I start?
So it's Stefano, your talk is not now.
It's not now, right? Yeah, so I was a bit confused.
No. Yeah, sorry for the confusion. Now we have the break. Just
okay.
Just wanted to test. Just test. Yeah, we have done it for others. So. I will start. Welcome everyone. Welcome back from the break. Now we'll um, hear from Yidong Zhu about the effects of small-scale absorption systems on neutral islands during the late Epoch of Reionization. Yidong, you can start whenever you are ready.
Sorry, I just unmuted myself.
Fine, you can start sharing again. And you have 12 minutes. I will give you a 2-minute warning.
Okay, thank you. Hi, everyone. I'm Yidong from National Astronomical Observatory of China. Here I'm going to talk about our recent work on the effects of small-scale absorption systems on neutral islands during the late epoch of reionization. Thanks to Anastasia for a very comprehensive overview talk. So we now have the whole picture of reionization process and the physics involved and the various ways to probe the epoch of reionization and the cosmic dawn using the 21 centimeter signals. Currently, substantial efforts have been put into measuring the global spectrum from the cosmic dawn and the 21 centimeter power spectrum from the epoch of reionization. We know that the Edge-Slow experiment have measured a deep absorption signal from the cosmic dawn, possibly from cosmic dawn, but the signal is much larger than the expectation from the standard model. Considering the shock heating, Compton heating, and the density fluctuations, the maximum expectation of the absorption signal from cosmic dawn is further suppressed, enlarging the discrepancy between the theory and the measured signal. However, the latest SARAS experiments have made a non-detection, and it indicates that the edge signal is probably not of astrophysical origin. So this signal is still under debate and needs to be further confirmed by independent experiments. On the other hand, many interferometers have achieved lower and lower upper limits to the power spectrum. And the Hera experiments have provided the stringent constraints on the 21 centimeter power spectrum from the reionization. With these observational constraints, the ultimate goal is to infer the physics driving the epoch, driving the reionization. Including the source and radiation properties and the sinks that absorbs ionizing photons. Here in our work, we focus on the sinks during the late epoch of reionization. The sinks are mainly small-scale absorbers, and they are especially important for the later stage of reionization because when the typical scale of the ionized regions is larger than the mean free path, then the propagation of ionizing photons is effectively regulated by these small-scale absorbers. And one complication comes from the fact that the effects of small-scale absorbers are similar to some of the source properties. So we need to find a way to break the degeneracy with the source properties. In order to model the small-scale absorbers, we use the semi-numerical simulation of island fast that is especially designed for the late epoch of reionization, and it can be used to cover a large parameter space. And here we focus on the effects of absorbers on the statistics of neutral islands because these effects are more important during the late stages. The goal is to find the differentiable signals that can be measured by the upcoming SKA low frequency array. And more importantly, we want to find ways to break the degeneracy between the effects of source properties and the absorber abundance. So this is our semi-numerical simulation, island fast. It is based on the island model. So before the percolation of the ionized regions, it adopts a similar algorithm as the 21 centimeter fast. But after the percolation, it adopts a two-step filtering algorithm. It first finds host islands with the island barrier, including an ionizing background. And then it finds bubbles in islands with the bubble barrier without an ionizing background inside these islands. So in the simulation, the small scale absorbers are modeled with mean free path parameter. So the intensity of the ionizing background is attenuated by both the large scale neutral islands as well as the small scale absorbers. Three absorber models are considered. The first is called the no SSA model, which assumes no small scale absorbers, and the ionizing photons propagation is completely limited by the neutral islands, and it corresponds to an extremely high level of the ionizing background. The second model is called the SC model, which is based on observations of Lama limit systems, and it corresponds to a moderate intensity of the ionizing background. The third model is the RS model, which is from the radiation hydrodynamic simulations, and it predicts the lowest mean free path that is more consistent with the recent measurements by Becker et al. 2021, and it corresponds to the lowest level of the UV background. For each of these models, we run two sets of simulations. The first one assumes early and low mass ionizing sources with a low ionizing efficiency parameter, and the other set assumes late and high mass ionizing sources corresponding to a higher ionizing efficiency parameter. So these are the results of the ionization fields. From top to bottom, we see the results from more and more abundant small-scale absorbers, and it is found that more abundant absorbers result in more numerous small-scale islands. So it reflects the competitive role played by the ionizing photons from the ionizing background and those from the sources inside the islands. So when the ionizing background dominates the ionizing photon budget, the islands would be easily ionized from these ionizing background. So the small scale islands would be hard to keep their identities. If the ionizing photons from the inside the islands dominate when the ionizing background is quite low, then the islands will tend to be disintegrated from inside, which results in more numerous small-scale islands and more obvious evolution in the island size. Then we apply the mean free path algorithm to extract the size of the neutral islands and plot this size distribution of neutral islands here. So it is found that during early and middle stages of reionization, the size distribution evolves obviously from larger scales to smaller scales. However, after the reionization enters the neutral fiber stage at the late epoch of reionization, the evolution in the size of islands becomes extremely slow in the no SSA model and the SC model. And during the island stage, they show a constant typical island scale at about 10 comoving megparsecs. However, if the abundance of the absorbers is quite high with a very low ionizing background, as in the RS model, we will see obvious evolution of the typical island scale throughout the late epoch of reionization. Also here, we can see the source dependence of this island scale with the more massive ionizing sources result in larger typical size in the islands. Then here we compare the size distribution among these three models at the same neutral fractions. Here, in the upper panels, the colored curves correspond to the three models with the same ionizing efficiency of 10, and the black dot dashed curve corresponds to the RS model with a high ionizing efficiency parameter. So with the same ionizing efficiency parameter, all the three models predicts the same ionizing, the same size distribution of islands at the beginning of the island stage. And as the neutral fraction decreases, we see that only the RS model have an obvious evolution in the size of neutral islands. And coincidentally, we see from the central panel that the RS model with the higher ionizing efficiency parameter predicts the almost identical size distribution to the other two models with the lower ionizing efficiency parameter, which shows the degeneracy between the source properties and absorber abundance. However, this degeneracy can be easily broken by measuring the size at multiple redshifts. So we can use the evolutionary behavior of the size distribution of neutral islands to break the degeneracy between the source properties and the absorber abundance. Here we also notice that the characteristic scale predicted by the no-SSA model is quite similar to the SC model, which indicates that the typical size of islands is not very sensitive to the small-scale absorber abundance, at least below a certain threshold. In order to estimate this threshold, we run several more simulations with varying the mean free path parameter. So this plot shows the relation between the typical island scale and the mean free path of ionizing photons. It is found that when the mean free path increases, the typical island size first increases and gradually saturates at about 9 kemoving megaparsecs. So our SC model roughly represents this abundance threshold in this case. And also from this plot, we can see that the small scale abundance can be effectively constrained by measuring the typical scale of the remaining neutral islands. Also, we compared the 21 centimeter power spectrum among these three models, and it is found that with the more abundant small scale absorbers, the island scale would be smaller, so that the large scale power in the 21 centimeter fluctuations would be suppressed. And also by observing the evolutionary behavior in the power spectrum, it helps to break the degeneracy between the source properties and the absorber abundance. Then we consider the observations with the upcoming SK1 low array, and to investigate the possibilities to distinguish these different absorber abundance models. First, we consider the imaging observation to generate the mock 21 centimeter images as observed by the SK1 low. We first smooth the 21 centimeter brightness field to match the SK resolution, and then add the thermal noise to the mock images. It is found that although with the higher angular resolution, the inner array of SK1 will have a high thermal noise. So the core array would be preferred for the imaging observations. So similarly, we apply the mean free path algorithm to extract the size distribution of islands from these mock images. So we found that if we observe with a narrow band imaging observation with a bandwidth of about 0.1 megahertz, we will be able to extract the intrinsic scale of the neutral islands during the late stage of reionization. However, if we use a broadband imaging observation with a bandwidth of about 1 megahertz, the thermal noise will be lowered, but the extracted island size would be significantly larger than the intrinsic scale. However, we can still see that in this size distribution evolution, only the RS model shows clear evolution in the size distribution. So although the size of islands is distorted, the evolutionary behavior is somewhat is still retained. So here we also consider the power spectrum measurement. Here we plot the 21 centimeter power spectrum with expected measurement error with the core array of SK1 low. So from this figure, we find that the differences between the different absorber abundance models are significant enough to be separated as compared to the measurement error. So in principle, abundance of the small scale absorbers and the level of the ionizing background can be constrained or distinguished by measuring the 21 centimeter power spectrum. So to summarize,
you conclude soon? Thank you.
Sorry?
Yeah, I was going to say, can you conclude soon? Fine.
Okay, so this is the last slide. So we going to summarize, we have investigated the effects of small-scale absorbers by using semi-numerical simulations, and we found that the absorbers significantly affect the morphology of the ionization field and suppress the large-scale power in the 21 centimeter power spectrum. And the morphology reflects the competitive rules played by the ionizing photons coming from inside and outside. And it is also found that the evolutionary behavior in the size distribution can be used to break the degeneracy between the source properties and absorber abundance. So this size evolution can be used to put constraint on the small scale absorbers and the level of the ionizing background. Thank you very much.
Thank you for the very nice talk. We already have some questions for you on Slack.
Okay, I will check it later. Sorry, are you hearing
me? It up here to stick and move. Thank you. Now we move on to the next speaker, Aishrila Mazumder. She will talk about end-to-end simulation pipelines for sensitive interferometric observations. Aishrila, you can start sharing your screen and start your talk. I'll give you a 2-minute warning.
Okay, thanks. Hi everyone, I'm Aishrila. I'm a final year PhD student at IIT Indore, and I thank the organizers for giving me this opportunity to present our work. So today I will talk about an end-to-end simulation pipeline that we have been developing for sensitive observations like those targeting the CD and EOR signals. And this work has been done in collaboration with the people that I have listed out here, along with many others. So just to give a brief overview, this graph, everyone is familiar with the schematic, but just for completeness. So when we are targeting 21 centimeter signal from EOR, this is the point where the signal is originating, and this region in blue is where we are sitting trying to observe the signal. So there's already a lot of intervening things that the signal is passing through before it comes to us. And this is also very beautifully demonstrated in this schematic where this is our signal, which is of the order of some 10 of millikelvin. Whereas when it's coming to us, it's passing through so many astrophysical foregrounds that are of the order of kelvins, which is like 3 to 4 times higher in magnitude. And this is typically the scenario in low frequencies. So this is the first obstacle that when we are trying to observe the 21 centimeter signal, we have to deal with. And then comes the instrument, because the instrument itself will introduce its own response into whatever we are observing. And this actually mostly has a common framework with which it can be described. But the thing is that as we change the instrument layout and we go from one instrument to another, the layouts, the change in layout, the change in electronics, the change in the surrounding conditions, a lot of it affects the observations. And so we actually need to treat it in a case-by-case scenario just to see that what instrument does what to our signal detections. And then there is this radio frequency interference that we all know is there when we are doing radio astronomy. And this is actually a very real image from a from an observation that we did at 150 megahertz, and as you can see, these channels are totally blanked with RFI, and so once we try to remove these RFI by resolving it with the high time and frequency, what happens is that we are introducing gaps in the frequency channels. So when this kind of gaps we propagate it to our path spectrum domain, we do get spurious structures that has the potential to actually suppress, obscure the signal that we are trying to detect. And then because we are dealing in the very low frequency regime, like UR science, we will do for anything less than 200 megahertz to say 80 megahertz, something like that. So this is actually a graph that we for SK low, and as we can see, the ionosphere itself, the electrons in the ionosphere, the total electron content, these gradients also induce errors in the phases of the observations, which might be detrimental to the sensitive observations that we are trying to detect. And unfortunately, this is not all. We have effects of imperfect primary beam modelings, the thermal noise, which is always going to be there no matter how much observation we take, and there are many more systematic, some of which we might not even know about. So this is kind of a very complicated scenario, and in such a case, with the advent of SK low, we actually need to see that if we really want to observe the signal with SK low, how each of these things will affect our simulations. Although there have been a lot of research into this, but still, if we keep SK in context, because every time we are trying to take an observation at low frequencies, we are coming up with some kind of new problems. So keeping all that in mind, we have kind of developed an end-to-end simulation pipeline. So the idea is that because our the sky brightness and the visibilities that my radio interferometer is actually measuring is not very simply related because of all the intervening effects that come. So it's better if we can just simulate it first and introduce the non-idealities that we know will be there, and to see how they are affecting the recovery of the signal. So this here is a schematic of how we have designed the pipeline currently. It's still obviously a work in progress. So in the current iteration, it takes an input sky model that consists of some realization of the 21 centimeter signal, and foreground model, which we are currently treating as point source foregrounds only, because synchrotron itself will introduce another level of difficulty, which obviously we are working on right now, but we haven't yet completed that. And the thing is that we can also introduce some kind of array layout. It can be for GMRT, it can be for SK, it doesn't matter, but thing is that we need to have the array layout ready with us. And after the first round of simulation, which we will do, saying that okay, everything is fine, this is the perfect sky, we can introduce some non-idealities in the simulations. So currently we have done for calibration error, where we have introduced some calibration imperfections, and we have also done for position errors, where this entire sky model that we have generated has some shifts in its position, so that we can see how this error actually propagates into our residuals. So this here is parameter set that we have used for the current realization, and it is done for the SK1 low core layout, which is around 200 kilometers from the central, 2 kilometer from the central station, which approximately gave a synthesized beam of 2.5 arc minutes with a 4-degree field of view. And this is the kind of H1 signal. So we have used simple 21 centimeter fast realization and projected it onto a sky model to give me a 21 centimeter signal. And this is kind of a DNDS plot, that is the point source distribution, which we have used to generate positions of the sources, of the extragalactic sources in the sky. And this is the telescope layout for SK1 low that we have used. And when we combine it and run our simulations, this is the kind of sky model that we get, which is kind of obvious, because it's not like we are going to see the signal when we will see the foregrounds in the first go. So we have to treat the foregrounds and then go on to the signals. So for that, what we have done is the first thing is that calibration errors. So this is roughly the calibration relation that we are used to. So if everything was ideal, this should be 1, but it's obviously not 1. So what we have done is varied it from 0.001% up to as high as 10% calibration errors, and see how it propagates into our path spectrum estimation. And as we can see that the higher up in calibration errors we go, the more it becomes difficult for the signal to recover, because our foreground starts to leak out of the wedge and into the window. So and when we turn this into the calculate the path spectrum, spherical average path spectrum from this, as we can see here that the red curves here that is shown here, these are the actual, if the sky had just signal, how the interferometer would observe it. And when we have around 0.01% calibration error, it's fine, it actually traces the signal. But as we go a bit higher up, what happens is that the residuals become so high that the signal cannot be traced. So this is something we have to be careful about when we are dealing with actual 21 centimeter observations using the SK. Similarly, we have used position errors where the displacements have been around started from 0.05 arc seconds all the way to 500 arc seconds. Like, it's a huge range just to see what happens. And we saw that around 5 arc seconds, which is a very reasonable amount of position accuracy that we can expect from telescopes like SKA. The signal recovery looks fine because it's consistent within the error bars of the recovered signal. But what happens is that as we go, if there is more imperfection, yeah,
it's like 2 minutes.
okay. So the more errors there are, obviously the signal gets suppressed, and when we go to as high as say 50 arc minutes, which is arc seconds, sorry, which is actually a lot of displacement for a source, the signal actually is not able to be is not recovered at all. So to summarize, we have actually produced an end-to-end pipeline for synthetic observations, because as I already said, that we actually have to deal with a lot of things before we can actually go to a stage where the signal can be recovered. And in the current iteration, the pipeline can incorporate position errors and calibration errors. And the sky model is a very realistic but simplistic one, considering that it consists of only point sources. And we have our results using not just SKLO, but for HERA MWA actually show that the optimal calibration error tolerance is around 0.01%, while the position error tolerance is 5 arc seconds. And another interesting thing that we found was that there was no real preference from one configuration to another. All the three showed kind of consistent performance. So actually we need to introduce now more complications like the ionosphere, primary beam, thermal noise, because this is a complete noise-free formalism, to check where these arrays stand against each other. But for this iteration, it seems that these is the optimal values are the same for all the three layouts that we have used. And we have also done some RFI excision routine and seen how they will affect the path spectrum plane. And what we found was that when the spurious structures that is introduced when we are doing some RFI excision can be lowered to a great deal using both clean and LSSA. But if we are doing some different flagging scenarios, it seems that this LSSA approach is working better than the clean algorithm. So, and we actually have, you can check out these archive paper. It's already there where we have reported these results. So thank you for your time.
Thank you so much, Astella. Very nice talk. I would want everyone to now ask their questions on Slack, and Ashrila, it will be nice if you can answer them in the Slack channel.
Yeah, sure.
Because in order to stick to the schedule, it will be nice to move on to the next talk. The next talk will be by Barun Maity on efficient modeling of cosmic reionization using script. When we can start sharing your screen and start
Am I
presenting
audible?
whenever you're ready. Yes, yes, you are.
And
I'll
is the
give you.
screen visible?
Yes.
Yeah. So first of all, thanks to the organizer for providing me with this opportunity to present my work. So I'll be talking about efficient modeling of cosmic reionization using script. So I'd like to start with a brief motivations behind the work. We know that reionization is still one of the less understood phases in the evolution history of the universe. So there are a lot of unanswered questions like what's the precise reionization end, the duration of reionization, and we don't even know exactly what kind of sources may have driven the reionization process. But the advantage we have is that there are a lot of observational probes which are going to come in near future, and this spans multiple wavelength bands. So ideally one would like to incorporate all these observational probes if possible simultaneously in order to constrain the reionization physics. The third one is the importance of thermal evolution, and it has been proposed quite a lot that the thermal history of the IGM can be a good treasure of the ionization field, and but it doesn't get the required attention. So we'd like to take a look at that. And lastly, we need an efficient reionization model, including various inhomogeneities during reionization process in order to get constraints on various uncertain physical parameters during reionization and correctly infer the observational data. So script is basically one of these efficient model. The acronym stands for semi-numerical code for reionization with photon conservation. So as the name tells that it explicitly obeys the photon conservation while creating the ionization maps. So it basically solves the problem of photon number non-conservation, which is in general associated with the excursion set-based approach, which are generally used in the community for semi-numerical models. And this photon non-conservation has some further consequences. So it produces non-convergent large-scale 21 centimeter power spectra with respect to the resolution. So whatever small scale physics you include in your simulation, the overall large scale features should be intact because this is going to be an observational probe in near future. So script basically solves this problem. And in this particular work, we basically try to model these three physical effects during the ionization. The first one, as I have mentioned, that the thermal evolution of IGM. So in order to do that, we need to basically solve this standard first order differential equation for each of the cell in our simulation box. And to model reionization heating, we need to introduce a free parameter TRE, which basically gives the temperature increment if we go from a fully neutral cell to the fully ionized state. The second one is the inhomogeneous recombination, which is well known. And in order to compute the recombination number density, we need to track the density evolution history and the ionization history for each of the cells. And to quantify the inhomogeneities in the medium, we need to introduce another free parameter, which is commonly known as clumping factor. The third one is the radiative feedback, which is basically a consequence of reionization heating. It basically suppresses the star formation in the lower Marcellus due to the excess radiation pressure coming from reionization heating. And in general, people model this with a temperature dependent minimum threshold mass. And it can be a gradual effect or can be a step-like effect, whichever the case may be. So now let's straight go to some of the results. So in this figure, we have shown the light cones for three cases. At the top panel, we have both recombination and feedback. In the middle one, we do not have any feedback effect, but have the recombination effect. And at the bottom one, we neither have recombination nor have feedback. So clearly we can see that recombination and feedback both delays the reionization towards lower redshift. And this is also expected, as this has been seen in earlier studies too with other semi-numerical models. And for this study, we have taken a constant, taken the similar ionizing efficiency parameter, which is a redshift dependent parameter, which we have used here. And we can also compute the temperature light cones, and we can see that it basically traces the ionization field quite well. But this temperature is not so useful if we want to use this as an observational probe. Instead, what is useful is to go for the temperature estimates at low density IGM. And from earlier hydrodynamic simulation, it has been shown that the temperature at low density IGM follows a power law correlation with the over density. So if we can measure these temperatures, we can in principle use this as an observational probe. So in this figure, we again we have shown the same three cases, and what we find that as we proceeds with the reionization, the power law correlation also strengthens, as you can see, and this scattered is coming because the different portions in the simulation box is ionized at different times. So the color bar is basically showing the ionizing redshift for different cells. And now we have just need to fit a straight line through these scatter plots and get this T naught and gamma. And we already have some estimates of low density IDM temperature around, let's say, 5 and 6, and we can compare our model parameters with this. So what is important from this plot is that we can check that already very high temperature models can be ruled out by the available observational constraints. So it can be a potential probe of the late phase of the reionization. And the other models are basically showing similar kind of trend, but in principle we can do a full parameter space exploration with this, which I'll show later. And the next observational probe is the well-known one. It's the UV luminosity function. It basically the number densities of galaxies per unit magnitude per magnitude or luminosity beams. And the main effect is that the faint end of the UV luminosity function is suppressed as an effect of radiative feedback. So this cyan line do not contain the feedback effect, but in this blue line, if we include the radiative feedback, it's suppressed. Right now, the observational constraints are not so stringent, but with the upcoming telescopes like JWST and so on, we should be able to distinguish between these models. And the last one, and probably the most popular one, is the 21 centimeter power spectrum, which basically traces the fluctuations in the neutral hydrogen field. And the main findings is that we can, in these plots, we have shown the large scale power spectra as a function of redshift at the top panel and as a function of mass averaged ionization fraction at the bottom. So the main finding is that if we include the feedback and the recombination, it suppresses the amplitude of the power spectra. So these two are important to take into account in order to correctly model the 21 centimeter power spectra. Now let's move to the most interesting part of any kind of semi-numerical models, is that we can do full parameter space explorations with these models. So in our case, we have basically 5 free parameters. So we model ionizing efficiency dependent quantities. So zeta naught is the normalization, and alpha gives the power law in redshift. Similarly, we take an escape fraction as a mass dependent quantity. F escape naught is the normalization, and beta is the index. And as we are computing the temperature increment, so we have this TRE as a free parameter. And these are the set of observational constants which we are using currently. There is the model independent limits on ionization fraction, semi-scattering optical depth from Planck, and we have the privilege to include the low density IGM temperature from this recent study, and we also include UV luminosity function estimates at 2 redshifts. And lastly, we also put a constraint that reionization is n by, let's say, 5.3, which is which has been suggested in recent times by Lyman alpha studies. And these are the results which we have got. So in this plots, we have shown the posteriors for two cases. In one case, we have included the temperature constants, and which is the blue one. And in the orange case, we do not have any kind of temperature estimates. So clearly, you can see that inclusion of the temperature data improves the parameter
2 minutes.
constants. Yeah, sure. And we also find that the reionization end can be constrained well with the temperature constant temperature data. And these are the plots for 200 random samples in our instance chains. At the top panel, we have shown the reionization history, and at the middle point, middle panel, it's the temperature mean density, and at the bottom, it's the index on the word density. And we can see that there are a lot of models which are allowed if we do not include the temperature constant. But if we see these blue ones, we can check that these models can be ruled out by the temperature data. And you can see that very early reionization end is also not preferable, is also not preferred by the temperature constants. So before ending, I would like to share one slide by describing the work which I'm currently doing. So the next obvious step is to include the 20 centimeter data in the parameter space exploration studies. So in order to do that, we need to do a comparison studies between the photon conserving model and the standard excursion set based approach. So for that, we take a simplistic approach at first. So we do not include any kind of recombination and feedback. And we generate mock power spectra independently from photon conserving model and from excursion set based model, and incorporate the realistic Hera noise on top of that, and check if the models can recover the input parameters. And we check it for two different resolutions. For the photon conserving case, we can see that it's recovering pretty well. For the excursion set based, it is quite good in the high resolution, but if we use the coarser resolution, and we can see that this red one is not in good agreement with the input parameters, and in some cases it is basically away from the, it's basically outside the 1 sigma limit. So in principle, this can be an important effect to take into account the photon conservation. So I'll summarize the work. So we have modeled the effect of inhomogeneous recombination using photon conserving script. We also probe the thermal history of the IgM, which is necessary to model the radiative feedback. And we check these effects on a variety of observables, and which can be used to pursue a full parameter space exploration with the available observation constants. And lastly, the photon number non-conservation can be impactful while interpreting the large-scale 21 centimeter data. So I would like to stop here, and if there are any questions, I'll take. Thanks.
Thank you, Barun. Very nice talk. We already have a question on Slack. So Joe Lewis asks, compliments you for a very nice talk, and then asks, have you considered constraining your models using observations of the opacity in the Lyman alpha forest? That would probably be more constraining than relying on HX1.
Exactly. There is an independent study using script which uses that aspect, but including this recombination and feedback effect, we are yet to check that. So yes, the obvious next step is to include that opacity from Lyman alpha forest.
Thank you. I have a quick question. So in your for doing MCMC, do you directly run your code, or do you use something like emulators or something else? Is script fast enough?
Yeah, script fast enough if we run it in a coarser resolution. So for this study, it is good enough. But yes, if we want to get the information from small scales like the 21 centimeter case, then we do that kind of thing, emulator or we have to interpolate or something like that, which we are yet to do.
One last question, maybe. Gerald asks, how do you calculate the heating? Is this parameterized with the TRE parameter?
Yes, exactly. It is. So I can show the slide. Yes. So this astrophysical terms basically contains the reionization heating, and which is proportional to this TRE parameter, and this will also be proportional to some of the factors which goes into the inhomogeneous recombination, like it will go as the square of number density and so on. So yes, the main thing is that we use this as a free parameter for reionization heating.
Thank you, Barun. Please ask more. If you have more questions, post it on Slack, and Barun, please answer them in Slack.
Yeah, thanks.
Now we move on to the final talk of this session. It will be by Stefano Camera, and he will talk about BAOs from H1 intensity mapping, the importance of cross correlations in the monopole and quadrupole. Stefano, if you can start sharing the screen, and you can start whenever you're ready. Yes.
Okay, let's go with presentation mode. So good day, everybody, whatever time zone you are in. My name is Stefano Camera. I'm staff at the University of Turin in Italy. And today I'm going to talk about this topic. So the cross correlation, the importance of cross correlation in monopole and quadrupole, the power spectrum, when reconstructing Baryon acoustic oscillations from H1 intensity mapping. I would like to emphasize that this work has been carried out mainly almost single-handedly by my former master students, Andrea Robiola, and we supervised by myself and Steve Cannington, who is also a speaker at this conference. You can find the preprint of the paper at this number of the archive, and it's currently under peer review and will be resubmitted soon. So the idea here is to use H1 intensity mapping as a cosmological observable. In this conference, surely I don't have to explain to you what is H1 intensity mapping, but since it will be in cross correlation with galaxy surveys, let's just emphasize the main difference. So instead of detecting objects, traces of the last case structure above a certain threshold, we just integrate the overall intensity of the 21 centimeter line in big pixels in the sky and measure a temperature brightness profile in the sky. We do this as a benchmark for cosmological measurements. We use Baryon acoustic oscillations. Baryon acoustic oscillations are due to the decoupling of matter and radiation in the early universe. And because of this, we have left with an excess probability in the detection of an overdensity in the last case structure at a given fixed size. So in this sense, this is a standard ruler akin to standard candles, for instance, if you want, with supernovae. This excess probability in the correlation function translates into wiggles in the power spectrum. Sorry, I would like to have some pointer or something like that. So we wanted to try and use the pointer from Zoom, but I don't seem to be able to find it. No. There we go. No, mouse. Possibly. Well, okay, whatever.
We are able to see your mouse cursor.
Okay, let's see if you can keep seeing it in presentation mode. Otherwise, I'll just talk. So probably not, but in any case, okay, let's just discuss. In this plot here, you see the log of the power spectrum, which is a Fourier transform of the correlation function as a function of log of the Fourier mode, corresponding Fourier mode. This is just the linear power spectrum you see on large scales, which are small k's, the primordial power spectrum, which is just the power law that goes with NS, the spectral index. And then we have about the radiation equality, the turnover of the power spectrum, with something that goes down like k to the n minus 4. And in those scales, which are about 10 to the minus 2-ish inverse megaparsec, h over megaparsec, you have the wiggles that are the Fourier transform of the peak of the Baryon acoustic oscillation in real space. So what we want to detect basically is those wiggles against a null broadband power spectrum. The problem is if you try and do so with an SKA observatory-like instrument, so intensity mapping with single dish from an interferometer, single dish mode from an interferometer. This has been assessed in this paper by Paco Villas-Navarro et al. In 2017. In this paper, in this plot, you see the power spectrum as a function of multiple in linear theory, which is black. When you convolve it with a Gaussian beam that corresponds to a resolution in the sky corresponding to 5 megaparsecs over h in blue, etc., different colors. And as you see, the effect of the beam, of the telescope beam on those scales makes the detection of the Baryon acoustic oscillations almost impossible. So this is why actually we want to try and do this in cross correlation with galaxy surveys, trying to recover some of the transverse information from the detection of galaxies separately. So the observed power spectrum, let me just guide you through it. So we have the multi-power spectrum. We can't observe the multi-power spectrum directly, so we observe tracers of the large scale structure. And so for a given tracer, the autocorrelation power spectrum, you can write it, at least on cosmological scales, as a bias, an effective bias, which is just a function of time squared times the multi-power spectrum. This is just in configuration space, but we don't observe galaxy traces in configuration space. We observe them in redshift space, meaning that at least in linear scales, we have to account for the distortions of redshift space. And this is the so-called Kaiser term. This is the term that you see in square brackets here that breaks the isotropy of the power spectrum. So instead of being just a function of k, the modulus of the wave number, you have that is now the function of k parallel, the k perpendicular. And mu here is the cosine of the angle between the line of sight direction and the wave mode k. Now, if you take two traces, for instance, H1 intensity mapping and galaxies, you have the cross correlation power spectrum, which is basically the same thing, but you replace each one of the various bias and growth, so the beta term that you have in the Kaiser term, with one from tracer 1 and one from tracer 2. So this is just the observed theoretical power spectrum, but then we have to account for the fact that there are observational effects and possible also systematic effects. So if we want to fold in such effects, for instance, we have to account for a transverse beam, which is what I was referring to before. So for each tracer T that is affected by a beam, you have to multiply by an exponential. If you account for a Gaussian beam, you have to multiply it for an exponential like this that goes as 1 minus mu squared. Then, if you also account for an uncertainty in the measurement of the redshift, you have a similar Gaussian uncertainty. You have a similar term for each tracer that is affected by it. You have a similar term that now goes as mu squared, because this is an uncertainty on the radial, so the parallel wave mode. And finally, we also account for the fact that there are observed volume and foreground subtraction effects for each tracer. This is affected by it. And so we multiply further by this function that you can find in various papers, for instance, by Steve Cannington, that accounts for the fact that you are removing some large-scale mode because of foreground subtraction. Finally, what we actually forecast the performances of different experiments on is the Legendre multiples of the power spectrum. So instead of binning the power spectrum in k parallel and k perpendicular, we integrate over this angle, this mu, and this is weighted by the Legendre multiple L with L. And given that the only power of mu, the largest power of mu is mu squared, we have only monopole, quadrupole, and hexadecapole. However, it is known that the hexadecapole has a very low signal to noise. So on this paper, in this analysis, we only focus on the monopole and quadrupole. So finally, this is the idea. This is the setup. So as I told you, to compensate for the low transfer resolution, we use complementary tracers, in this case galaxies, for a Euclid-like survey. We focus on the monopole and quadrupole in the redshift interval between about 1 and 2. And this is because these future galaxy surveys like Euclid will be focusing mostly their spectroscopy in that redshift range. Andrea simulated 100, well, created 100 log normal simulations with this size and included also thermal noise, shock noise, and radio foregrounds. And we performed a blind foreground removal via a simple principal components analysis. This is like a simplistic way to assess foreground removal, but for the setup of this analysis is more than enough. We tested that. And the methodology we used was just looking at the delta chi-squared, basically, between the model and the null hypothesis. The model that we use, we took it from the paper by Paco in 2017. So basically, we take as a template a broadband power spectrum with no wiggles, which is this NW. And then we sum it with the difference between, well, basically, we add wiggles on top, and these wiggles are take into account the so-called Arcos-Paczynski effect, the fact that to recover the 3D position of the galaxy, we have to infer it from the redshift. So we have to assume a fiducial cosmology. This fiducial cosmology, if it were wrong, would create distortions in the pattern that we measure in the sky. And these distortions can be parameterized by these alpha parallel and alpha perpendicular Arcos-Paczynski terms. We compare this template in the simulations against the null hypothesis of no BAO. So in this case, we just have a broadband, no wiggle power spectrum. And the parameters of the model, the parameters which fit for, are both cosmological parameters, observational parameters, and nuisance parameters. In particular, cosmology is encoded mostly in the Arcos-Paczynski terms, alpha parallel and alpha perpendicular. Then we add the bias for galaxies, the effective bias for H1, which is actually the bias of H1 multiplied by the right-hand temperature of the sky at that redshift. This is an effective bias because the two quantities are not, we cannot tell them apart. So it just acts as an overall bias. And then we also include a resolution of the instrument and an uncertainty in the redshift. So R and sigma, capital R and sigma R. Finally, there are these two nuisance parameters perpendicular that account for the box size of the simulations and the foreground removal. Yeah, there's a question?
Yeah, 2 minutes, 2 more minutes.
Okay. Okay, let's have a look at how some of these simulations look like. This is, you see the BAO, the Baryon acoustic oscillation in the power spectrum multiples. This is just for the monopole and the auto correlation of neutral hydrogen. So this is the power spectrum multiple or neutral hydrogen with itself at two different redshifts, 0.9 and 1.35. And basically you see here the ratio of the wiggled versus non-wiggled power spectrum as written in the y-axis label. So the red is the no-wiggles, the blue is the wiggles. And basically, by eye, you could tell that at least at low redshift, there is some room for like a slight detection of the BAOs. The data sit with arrow bars on the blue curve, but they're not. It's not very easy to tell them apart from the red curve. And if you increase redshift, given that the resolution, the angular resolution decreases with redshift, I mean, yeah, exactly, decreases with redshift, you see that it's much harder to detect BAOs at high redshift. There's even been a two that I'm not showing here where basically you can't see anything. But now let's have a look at what happens when you have the cross correlation. And here, thanks to the fact that the galaxies add some resolution in on angular side, although they bring some low resolution because of redshift uncertainty on the transverse modes, it's much, the situation looks much brighter in a sense because wiggles can be clearly seen with respect to the autocorrelation. This translates to the fact that if you look at the delta chi-square for the simulation, so basically in a way, how many sigmas away are from the fact that no detection has been made. In the autocorrelation of H1 for the different redshift bins, the distribution of the delta chi-squared isn't very far away from delta chi-square of 3. So it's the number of simulations that are above, detections that are above 3 sigmas is not very large, but these histograms are further apart in the case of cross correlation, meaning that it's easier to detect. And this is summarized by this in this table here, where you see for in the various rows, you have autocorrelation and cross correlation at different redshift bins. And if you focus on the inset that I highlighted in red, you see the number of realization, the percentage of realizations that are above 3 sigmas for the autocorrelation and cross-correlation, and basically cross-correlation is always higher than autocorrelation, and also it decreases with redshift less than what happens for autocorrelation. This is so in this way we can see that basically you gain by cross-correlating. Then we also had a look at the quadrupole. This was all for the monopole, but let's also have a look at the quadrupole. And in this case, you see the comparison for just one redshift bin on monopole and quadrupole. And basically the effect is that even though the error bars for the quadrupole are larger, so the signal to noise is smaller, the signal seems to be less affected by the beam, the transverse beam for the kind of the quadrupole. So this tells us that actually if we could include both of them, we would gain. And this is actually what you see in this slide, where you have the joint fit for monopole and quadrupole for the various parameters that in our analysis, with only monopole for the cross-correlation in blue, only quadrupole for cross-correlation in yellow, and both of them jointly fit in red. And basically you see that the contours are not biased, which is very important, and are tighter for the joint constraints. So to conclude, I don't know how fast I've been going, but just to conclude the point, the main take-home messages of this analysis that there is a very good to very good BAO detection significance for the monopole and quadrupole alone at low to intermediate redshift, and basically that autocorrelation and cross-correlations are complementary in a sense, and yet you want to use both. There is an additional benefit from joint fit, so the detection significance goes up to about 10 sigmas, which is very good. We also find a good validation of the analytical uncertainties that we used in the simulation with the data, meaning that at least for this setup, the Gaussian covariance seems to describe the data well enough. And finally, we found as expected, the detection significant decreases with redshift because the factor of the beam is larger, and this implies an added value of cross correlations because you can mitigate at least this effect a bit if you use cross correlation, and if you use both of them, all the better. So this, with this, I have concluded.
Thank you, Stefano. Very nice talk. As I don't see any questions on Slack yet, I have one question. So I have a very naive question. So you, so for the, you said that you are using a very simple foreground cleaning method, PCA method. So will your will your results improve if you use a better method for the auto power spectrum case, or is it very close to the primary beam? That's why it's difficult with just auto power spectrum.
So I would say that for the setup and the simulations we run, which are like simple log normal simulations and the kind of foregrounds that we injected, this method should be enough, and we shouldn't gain much by having like a more refined, more sophisticated foreground removal method. Of course, if we had to run the same analysis or more sophisticated simulations that are more realistic, then definitely we would gain by having like better foreground removal.
Thank you. Please post your questions on Slack, and Stefano, it would be nice if you can answer them in the Slack channel.
Sure. Got it.
Okay. This brings us to the end of this session. I would like to thank all the speakers and all the participants for joining in. Please continue your discussions with the speakers in the Slack channel. The next session of the day will be in about 1 hour. It will be on theoretical and observational constraints. Till then, thank you.